All right. So I'm going to start chapter 5 today. Chapter 5 is an extension of chapter 4, where we have the jump process. So we have already discussed the Levy process as our canonical candidate in the theory part for financial stock price jumps. Now in the numerical part, when we are using numerical approximations, we have already done it for the smooth models, the diffusion models in chapter 4. Now we will look at the jump process related models and do their numerical approximations. Obviously, we are going to lose the nice differential equation structure. The differential equation will be there, but it is now going to be augmented with a integral. The integral to take care of the jumps, because they are discrete in nature, so you cannot write a differential for them. And numerical approximation of that integral will be our additional task in this chapter. So a little bit of recap before we move on to the numerical discussion. What is our setting? The setting is our infinite activity pure jump Levy process. Levy process we have already formally defined earlier in chapter 1. So we will recall some of those. So we are trying to describe the dynamics of the asset's log price, incorporating jumps in the stock price process. The most well-known models in this area are due to Barndorf, Nielsen, and Shepard, which we have discussed, and the Kargem, Madan, and Yor model, CGMY model. Also, we can talk about the variance gamma model. These are the common canonical models incorporating jumps, and we are going to talk about them in our numericals. So in this chapter, what is done is it develops a procedure for pricing options. Of course, options is our simple contracts, call or put options, or some exotic options, path dependent options. We will do that when the underlying asset price dynamics are given by pure jump infinite activity Levy process. And the method will be illustrated using the CGMY, which is originally discussed in section 1.2.8, but one can also adopt it to the variance gamma. So CGMY will be our standing example, but we will see that we can also accommodate the variance gamma demonstration along with this. But one standing example is good enough to illustrate the method, and I am not going to go into a lot of details now. We will be talking about relatively simpler situations and one or two standard methods. There are, of course, many more complicated situations where jumps may occur and options may need to be priced. We will not get into the full detail. And also there are situations where there could be other distributions involved and different kinds of algebraic manipulations come into play. So that is more of a matter of detail, and let us focus on illustrating the method using some simple contracts and one canonical stock price process. What will happen is we will derive a partial integro differential equation. This integro part is for the jump. Then we will see how this PID is discretized, because we are going to do numerical analysis. And obviously, we'll develop the numerical scheme. So it's like we'll develop the algorithms like in chapter 4 for computing approximate solutions. And of course, again, the initial conditions, boundary conditions, they will have a role to play. We will have to explicitly state those conditions and show how they are going to be incorporated in the algorithm. So that would be the agenda of this chapter. Okay, so let us go back a little bit and start from the basic equations, generating equations. So as we have discussed in chapter 1, section 1.1.8, if you recall, a Levy process is a stochastic process with stationary independent integrals. And we have this Levy-Khinchin theorem, which characterizes the Levy process in terms of an explicit characteristic function. So the definition goes as follows, that there exists a measure nu. Nu is the measure such that for all real u and non-negative t, so we can think of this u as the price process and t as the time. The expectation of iuxt is given by e to the power t phi u. And now this phi is no longer our nice normal distribution phi. It is the Levy phi, where phi u is given by this function as in equation 5.2. Now, this is where the departure from the diffusion process comes in. The first two terms here are well known. The first two terms are exactly the normal distribution component, the smooth part. The last term, this integral term, is the new one, which is the contribution from the jump process. So what we will need is, we will need a measure nu, which will admit, hopefully, which will admit a density. And this part here is the correction part for the jump process. I say correction because when we are incorporating jumps, the jump will have its own average values. So that will have to be adjusted with the original average value of the smooth part of the process. You remember that when we started discussing about characteristic functions, we also talked about how to look at the characteristic function for the mean-centered random variable. So mean adjustments are often important for us. We have to adjust for the mean, and that will have to be done in this case because we have this jump process. Is this clear so far? What we are trying to do? The theoretical definitions I am just repeating from chapter 1, but now the purpose is slightly different because we want to move on to numericals. Is it okay so far?
Yes, sir.
So just to complete the formal definition, here this gamma and this sigma are real numbers. Nu is the measure on the real lines such that it is 0 at 0, 0 at the origin. It is defined on the whole real line, but 0 at the origin. And nu is such that this integral of the minimum of 1 and x square over d nu x is bounded. This is crucial. We discussed it earlier also in chapter 1, that this is crucial for all these adjustments to be admissible. When we are working empirically, of course, we will work with an explicit density. Then we will choose our density in such a way that such conditions are satisfied. But in theoretical terms, in a general definition setting, this is an important condition. So this integral of minimum of 1 and x square dx must be bounded. Can you tell me where you have seen this before? You all have seen this before. In probability. Anyone here who would like to respond? We have seen
Finiteness of second order moments.
second order moments. Can you recall an inequality which is usually taught in our first or second year in undergraduate. Inequality on probabilities. Okay, so we'll come back to this. So probably we'll need a few minutes to recall, but we have seen similar things. Okay, so this is a required condition on the measure nu. We assume a Levy process of this form in particular, where xt is given by this r minus q plus mu t plus zt, where r minus q is known. These are the interest rate and the dividend rate. Mu is the mean part of the drift term, which I can control. Control in the sense I can make the adjustment to the mu. This far it is as usual, but then we throw in this additional pure jump component z. So again, if you recall this section 1.2.8, this section here, we have had this discussion before, that we have the drift part where I can make adjustments through the parameter mu, and I throw in the pure jump component zt, which is going to give me the jump process. In particular, we also talked about this explicit density for the Levy measure, that suppose the Levy measure associated to this zt can be written as d nu equal to ky dy, where ky is an explicit density function. This density function we have talked about before, and this will be our standing example in this chapter. Where so this is our standing example, as I said, where I have this particular parameter capital Y, this particular parameter capital Y, which has a big role to play. So first of all, the density is defined in such a way that it is defined in two parts, one for the positive jumps and one for the negative jumps, where the intensity rate is given by lambda p and lambda n. But it doesn't end there. There is also a scaling factor in the denominator controlled by this parameter capital Y, which we will talk about. So this is capital Y as in CGMY, where lambda p and lambda n are explicitly written in terms of the parameters of the model, theta sigma nu, like this. Okay, so I'm not showing you something new here, by the way. We are just recalling this density example. We have discussed it before in chapter 1. But now I want to talk a little bit more about the parameter capital Y. So this variable capital Y, which I can choose, this allows for the control of what is the sign of our large and small jumps. So we are differentiating between large jumps and small jumps on the positive side, on the negative side, and how it can be controlled. So if I raise Y above 0, if I make Y positive, we can induce greater activity near 0. Because when Y is positive, you see this term will go to 0 faster, both of these terms. So I induce more activity near 0 and less activity further away from 0. In particular, these are some critical values of interest in terms of this capital Y parameter. If capital Y is equal to 1, which means the power of Y is square, this is Y square in both sides. Capital Y equal to 1 separates the finite variation cases where Y is less than 1 from infinite variation cases. So y square, whether the power is less than 2 or more than 2, that will separate the finite variation and infinite variation cases. Y equal to 0 separates the finite arrival cases where y is negative and infinite arrival cases where y is positive. And finally, y equal to -1 is another value of interest, another critical value, because if y is -1, then this denominator becomes y becomes independent of y. So when y is less than -1, it means the activities are concentrated away from 0. So I have more activities further away from 0. Because if y is less than -1, then the power of y in the numerator becomes positive. So 1 plus y is negative. So it basically comes to the numerator as a positive exponent on both sides. And when y is greater than -1, so I actually have some power of y in the denominator, then that is the situation where I have activity concentrated at 0. So when the denominator becomes big faster, the activities come close to 0. And when the power of y is reduced, the activities are spread further and further. So I have more activities away from 0. That's the usual characteristic induced by this type of a function. And then I have this finite and infinite variation depending on how big y is. Okay, all right. So does it make sense? All of these cases may not be immediately clear, but intuitively, at least, if you look at the shape of this density function and look at these possible, look at these critical values, you can understand the possibilities. When the power of y becomes negative in the denominator, or it becomes 0, or it becomes positive, we understand the concentration closer and away from 0. When this power is very big, we know that the density will fall away very quickly on both sides of 0. And if it is quick enough, then there is very little activity going further away. So if y is greater than 1, we have the infinite variation case, and less than 1 is finite variation. One can also distinguish between arrival rates, finite and infinite arrival rates. And the separation is at y equal to 0. So the power of y, the power of small y being more than 1 or less than 1. So let me just quickly recap. So we are talking about a particular density function choice for our Levy process. The pure jump component density is given by this ky of this particular form, the CGMY form. And we discussed about the importance of the parameter capital Y and what happens when capital Y is in a different range of values. Okay, so far, or any questions at this point? All right, so let me move forward. We will come back to this boundedness of this integral, where you have seen this before, but let me move on. Now, we have to look at the derivative pricing. So we have the generating process with particular density. Now let us start the derivative pricing problems. We have to look at the derivative pricing expression and then slowly build up our numerical routine. So let VSTT be the value of the derivative security at time small t, depending on the stock price. We can use Ito's lemma on the discounted price. So using Ito's lemma on the discounted price, if we are in this setup where I do have a jump part, then this expression will give us the whole derivative price expression. The first part is just the initial value. The second part is the part due to the del V del S term. This is the smooth part. This third term here is the jump contribution. And how does the jump contribution work? We are looking at a jump at, say, time t, then we are making an adjustment in the value with a stock price process just before t, where mu is a counting measure for the jump. And then when I have incorporated a jump, that automatically changes the average of the process. The drift term, the average expectation term, that changes. So that has to be adjusted back. So to make that back adjustment, we have an adjustment term here. This last integral, which centers our mean back to the original level. So I have the smooth part, I have the contribution of the jump being incorporated in the price, and I then make an adjustment for the mean. So this is how the application of Ito's lemma works here in the context of a jump process. Any questions? Is this clear? So can we move forward?
Yes, sir.
Okay, so now we are doing some adding and subtracting in this second step here. So let us look at this, because this is, as I said, today morning. So this is a bit of dirty algebra. So we have to be careful how we are manipulating terms. So in the first term here, so this is the initial value, it remains as it is. In the first term here, in this integral, what we do is, instead of just looking at DST, we make the mean adjustment. So we subtract this term R minus Q STDT, which is the drift term in the original Brownian motion model. So this is like as in trying to make terms as mean zero. So if I subtract it from here, I have to put it back. So I put it back in the adjustment term. So in the adjustment term, I put back this R minus Q STDT. So the total term here will come with the del V del S, because there was a del V del S here, and the same time discount. So we just add and subtract the same term to make it balanced, so that later on we can make arguments to solve some of these terms. Some of these terms we will try to simplify analytically, so that our final numerical routine is as simple as possible. So we again have the smooth part in the first step with a mean adjustment, the jump part in the second step, and the adjustment in the third step, now along with the mean center. So as I said, so mu is our counting integer valued random measure, which will count the number of jumps in any interval. The density nu dy dt is the compensation of mu, because we make the adjustments. So what we will do is, so recall that nu dy dt later on will come with a explicit density, but for now we can work with the general expression. So the new dy dt term here, we will put in the appropriate places. So in add and subtract this term, this whole integral to the equation here. This is our new dy dt, and the integrand is of this form, as in here, because this is my adjustment for the counting measure. So it's the same integrand with the new dy dt measure. So this is called a compensator in PD or PID literature. So what happens? So I have this additional term. So again, my first term is the usual smooth part. My second term is now two parts because I make the adjustment from mu dx dt. So I subtract mu dy dt here so that the compensation happens. But I have made the compensation by subtracting this whole thing. So I'll have to put it back. So now I have a new third term, which is putting back this mu dy dt integral. And the last term is, as before, the adjustment from the earlier step. So I have this additional term here introducing the compensator. So symbolically, this is straightforward, maybe tedious, but straightforward. But conceptually, what we are doing is we are adjusting for different parts of the process. We are adjusting for the drift in the continuous part. We are adjusting for the average contribution of the jumps, and we are also adjusting for the final counting density. We call this a random integer valued random measure in this last part with our new dx density function. So each term, each component, so to speak, each component sort of becomes centered. Why do we do that? So we do that because we want to simplify some of these terms so that our numerical algorithm is not unnecessarily complicated. So how do we go about simplifying? Now, let us consider a risk neutral measure Q, risk neutral probability. If I take expectation under a risk neutral probability of this derivative price, all these terms here, what I will get is the following. The first term will remain as it is. There won't be any change in this term, obviously. But because of this expectation, some of these terms will vanish. Can you tell me which terms are going to vanish? Can you look at this carefully? Think of the risk neutral expectation. We know what happens under risk neutral expectation. Under risk neutral expectation, the stock price can only give you the bank rate. So what are the things that are going to vanish and why? The final expression is there, so you can see which terms have vanished, but can you also reason this? Let us look at these terms one by one. This first integral here in the first step, if I take the risk neutral expectation, I claim that this will vanish. And I also claim that the second step here, because it is already mean centered through this compensation, this one will also vanish. So two compensated integrals, compensated as in mean centered integrals, they will vanish under the risk neutral expectation. And that's why we did the mean centered. The other terms will remain for now. And those terms, this is just a collected form of the same term. This integral here and this second integral here are gone. So I am left with this third integral and the fourth integral. But now I can see that there are some similarities. So we collect those two within a common expression.
Sir, why the first integral is 0? Because there is this del v del s term,
Yes.
but when we take expectation with respect to the stock price, then I understand that the second term is going to get it to 0,
So
but the
second,
first term is also there, isn't it?
but even with this del v del s, this will be 0. This is the same risk neutral portfolio construction argument. If we think of the simple Black-Scholes, we use the same argument there also.
Okay, sir. Okay, I got it. Yeah.
That's in fact this one is trickier to understand, but this is basically a sort of by construction 0 because I have compensated for the continuation.
Yes, sir.
The first one is where you argue with the original Black-Scholes type argument. The other two, it is just a rewriting. So these two terms are the same as in now below. Here, they look different, but they are the same term. Okay, but these two terms are the ones that will vanish if I have a risk neutral expectation. So this is where we are under a risk neutral probability. So we have got rid of some terms, but there is some more complicated terms still present. So we need some more arguments. So what is the first argument? The first argument is, and that is the most important one, we know that under risk neutral probability, the value can only grow at the bank rate. That's how risk neutral probabilities are defined. So any contract, the value can only grow at the bank rate under risk neutral probability. There is no other choice. So we force that. If we force that in our derivative pricing equation as of now, here, we will see that this additional integral, double integral part that we have put up here, that must be equal to 0. Because if the expectation is equal to only the first term, the second term has to be 0. That's the argument that we make. And then the second part of the argument is that this integrand inside the second bracket here. So if you ignore the dt integral part, this whole integral inside, you can argue that this integrand is non-negative. One can argue that this whole term within the second brackets, pair of second brackets, that is non-negative. And if I have the integral of a non-negative term, because the other term is also non-negative here, this e to the power, if the integral is 0 for a non-negative term, then the term itself has to be 0. There is no other choice. So this equation then forces this inside integral plus whatever else term, everything within the second bracket, to be equal to 0. So there are two parts to our argument. The first part was that this expectation is exactly equal to only the first term here. So the second term must be equal to 0. And the second part of the argument was, within this second bracket, this term we can argue is a non-negative term. And because the whole integral is 0, then the term inside has to be equal to 0. So these two pieces of argument actually finally gives us the equation that we are looking for. So finally what we write, that the PID that we are looking for, the integral differential equation that we are looking for the generic Levi density mu, or the explicit function ky dy. So here I have written nu, that was the generic generic notation. I can also substitute it with our explicit choice of density, as in here ky dy, to write the final target PID as in equation 5.5. So equation 5.5 is just rewriting this equation here, replacing nu dy by ky dy, when we have an explicit density function available to us. Okay, so we will take a break here, and when we resume, you think about this, how these expressions are derived, etc., because there are some involved arguments going on. Think about that, and also let me know where you have seen this kind of an equation before. Okay, so let us go back to the beginning. We started out with this setting of the Levy process driven jump in stock price with mean adjustments as and when required, and an explicit density as in 5.4. We talked about what is the implication of different values for this capital Y parameter. It separates different finite and infinite variation and arrival rate cases, as well as concentration of activity. Then we wrote out the modified Ito's lemma for this setting and use the risk neutrality arguments to finally eliminate some of the terms and arrive at this PIDE with an explicit Levy density if available. So any questions so far? On the way, I mentioned that this condition here, this boundedness of this integral condition here for the measure nu is somewhat familiar to some result in probability that we learned in our undergraduate days. Now, can you tell me what is that? Do you remember some result where for any probability distribution we showed that probability of the range outside plus minus 3 sigma must be less than 1/9?
Inequality.
What inequality?
Chebyshev inequality.
Yes. Yes. So can you now recognize this integral? Do you remember how that inequality was proved?
By constructing some indicator variable like mod xi minus mu by sigma greater than k, indicator of that.
Correct. So that it becomes flat outside that range. Remember?
Yes, yes, yes.
So this integral is actually doing the same thing for the interval plus minus 1.
Yes, yes.
The same idea. So that's why I thought that you should be able to recognize this. And the role it plays in this density construction is the same. Okay. So are there any questions regarding this final 5.5 equation? Because this is the one we are now going to use. So this is like our Black-Scholes for the jump process. This is the Black-Scholes counterpart for the jump process situation, which we will now tackle with numerical routines. So are there any questions on this? Okay, so if you are okay with 5.5, then we move on to the numerical part of this. So, okay, so 5.5 is our target for PIDE. This is the PIDE we wanted to set up. And we are going to solve this numerically for the particular Levy density as in here in 5.4. This candidate we will be using to make explicit numerical calculations. And as before, we will make this change of variable. So we will use log stock price. So we'll define X as the log of stock price and we reverse the time. So with an abuse of notation, I will write this. Sorry. What have I done? So that should be tau. Where are those? Tau. Okay, good. So we did similar things in chapter 4. So we write time in reverse and we use the log stock price. So with these new variables x and tau, we can rewrite our PID as in 5.6. So what have we done? We have defined W of x tau as VST. So there are two changes. S goes to log S and T goes to capital T minus T. So that the derivatives are going to be related in this way. So del 2 W del x square x tau minus del W del x tau will be this quantity. Del W del x is this and del W del tau is this. And W of x plus y and tau, we will write it as Vs e to the power y t, because we are using the log transformation. S is e to the power x. So with all those changes, my PIDE can be rewritten in this form. So I had this del V del T del V del S terms here. They become del W del tau and del W del x after the change. The terms in the integrand here, they will also be redefined, and the redefinition works in this way. I have this Wx plus y tau, Wx tau, ignoring the boundary parts. That the notation we have simplified. The boundary part we are ignoring for now. Del V del S comes to del W del x. And now this is 5.6 as the redefinition of 5.5. We are using all the substitutions and the derivatives are related in this way. So this whole set of equations are how the derivatives are related to each other. Okay. Can you confirm that this is fine? So these are variable changes. So the derivatives are reworked. So VST becomes Wx tau. So all these derivatives del to V and del V del S terms are redefined. Del V del T just changes sign, and this V goes to W. So is this okay? 5.5 getting transformed to 5.6 with the changes of variable.
Yes, sir.
So we are back to somewhat familiar region. We have a equation which is not a purely differential equation with an integral inserted. So this integral has to be handled with care. So earlier, all we needed to worry about was whether to use forward or backward or central difference to get a good approximation of the differential terms, the derivative terms. Now we have to be a little bit more careful to approximate the integrals properly. Because in integrals, errors of approximation also gets magnified over the integration process. So the approximation must be done very carefully for 5.6. So, okay. So again, we start with simple vanilla options. For illustration purpose, as I said, we will talk about simple options. So we will talk about the European put and European call. Now in our change notation, the put payoff will be given by this and the call payoff will be given by this. So e to the power x is nothing but the stock price, because we are working on the log transformation. So we will talk about pricing these two contracts and proposing to use the Neumann boundary conditions, which is directly on the derivatives. So recall that the Neumann boundary conditions were defined for these derivatives on the S and T system. Because we have changed our variable, the condition will now be on the X and tau system. So the condition on del 2V del S square or del V del S, they will become like this. So this one is actually coming from del 2 v del square. So the condition is written like this, that when x goes to minus infinity, which means stock price goes to 0, the second derivative condition is in 5.9 for all tau, all time points. And when stock price goes to infinity, x also goes to infinity. This is also taken to be 0. So remember, in Neumann boundary conditions, we impose the boundary conditions directly on the derivatives. And typically, they are taken to be 0. That's what we did in chapter 4. So we continue with similar arguments. Okay. So we have our new equation 5.6. We have these contracts to talk about. And we are going to use the Neumann boundary conditions, which will now look like 5.9 and 5.10. Of course, there will also be an initial condition, but that is easy to write. So before we start discretizing 5.6, because that's what we do, we transform a differential equation into a difference equation. As I said, we have to take care of the integral first. So we look into the evaluation of the integral term, because that is the additional complication we are facing now. So, of course, there are various approaches to evaluating integrals numerically. You have all done things like the trapezoidal rule, Simpson's rule. Yes, we have discussed this before in this term earlier, that what are the common numerical integration routines. Okay.
Yes, sir.
So we will be approaching one of those things, one of those techniques, and use them here suitably. But because these are improper integrals, this equation, this integral has infinite range. So we need to take a little bit more care. Because of course, as soon as we are doing finite numerical analysis, there is no infinity. So we have to select our upper limit and lower limit sufficiently large and sufficiently small to approximate plus minus infinity. That's one thing. And also we need to understand how this integrand behaves for very large or very small values. Because if the integrand is very sensitive, then the integral will be even more sensitive. So approximation will take more care. So the integral term here, this thing picked up from 5.6, is the one that we are going to work on. Now, by definition, the Levy measure ky dy is singular at y equal to 0. Remember that the candidate measure that we are talking about has a singularity at 0. Because nu 0, the singleton 0 had 0 mass, and the definition of the density was for strictly positive y and strictly negative y. So we did not define it for 0. So there is a singularity at 0. So when you are doing numerical work, we have to make sure that we skip a small interval around 0. The small has to be suitably small so that we are not missing out on some relevant segments, relevant positive or negative segments, but it also has to be reasonably long so that the singularity at 0 do not create trouble for us in the neighborhood. Because after all, we are going to do numerical approximation. Is the point clear? Why we are talking about this 0 point? Because we have a theoretical singularity.
Yes, sir.
The singularity usually doesn't lead to any problems. We handle it suitably, integrability problems or any analytical problems. So for the purpose of evaluating the integral, what we do is we split this whole region into two parts. One part is the part away from 0, mod y is greater than some suitably chosen epsilon, and the other part is the small interval around 0. So mod y is less than or equal to epsilon. So basically we split it into the bad part and the good part. The good part we will handle separately. So the whole integral, this whole integral here is now written in two parts. One part for this interval around 0, where we have this potential trouble has to be handled, and the other part which is away from 0. Now, in numerical analysis, we have to choose our epsilon, and the usual choice for the epsilon would be the grid size. So the grid on the log stock price now, x, we have to choose the step size as say delta x. So the natural choice for epsilon could be delta x. So we talk about the interval minus delta x to plus delta x separately, and the remaining part outside in the mod y greater than epsilon in equation 530. So the Levy measure for different processes behaves differently near 0. So we have to take note of that. For instance, if I am talking about the CGMOI process, the Levy measure for CGMOI process approaches infinity much faster than variance gamma. So CGMOI is our candidate. This was our standing candidate. And one can show that the approach to infinity will be faster for CGMOI compared to variance gamma, because there are free parameters there and which can make the convergence faster. So for this reason, we should have the highest possible order of approximation for the integrand near 0. So when we are talking about this small interval, even in that small interval, many things can go wrong. So we should make sure that our approximation is very, very precise in that small interval. So integrand is this term, where whatever is inside, this has to be approximated very closely for the small interval around 0. So let us talk about that region. So mod y less than equal to epsilon. What we do is from the integrand, we add and subtract y del w del x. So the original integral is written as this w terms minus y del w del x. Then I have this term where to adjust for this y del w, I insert another minus y here. Why am I doing that? So again, I am going to take the help of Taylor series, and I am adjusting for Taylor series terms. How does that go? So for these first three terms together, notice the wx plus y tau, if I use the Taylor series around the point y, I will get wx tau, y del w del x. The second term would be y square by 2 del 2 w del x square, and the order and the approximation will be of the order of y cube. So we are expanding wx plus y tau around x. X is the fixed point. We are expanding. So second order approximation, I am considering up to the second derivative here. And this is the error. And e to the power y, the other term here inside is, of course, if I do the Taylor series, I will get this term. So I take second order Taylor series approximation for both wx plus y tau and e to the power y, where my variable is y, of course. These are the two expansions which I will put here. If I put them in this equation, what I will get is the following expression. So remember that wx plus y tau minus wx tau minus y del w del x, because these two terms can come to the left hand side. If I put them together, I will be left with this del 2 w del x squared term. Similarly, here for e to the power y expansion also. So what I do get is, in the integrand, what I do get is this del 2 w del x squared y squared by 2 term, then this term for the e to the power y expansion, y squared by 2 del w del x again, because it was outside, and the error of approximation, the order of the error, y cube. So my original integrand for the interval around 0 was rewritten by introducing this term in between. We introduced it to facilitate the Taylor series expansion. We do the second order Taylor series expansion, adjusting for this. So then adding, subtracting, what we are left with are these two terms along with the order of error. Okay, so far?
Yes, sir.
And then obviously our numerical approximation, the approximation would be where I just ignore the error term. So my approximate value of this whole integral is given by this integral now in 550. So I originally had the w function and the e to the power y function. I substitute both of these using Taylor series approximation, and what I get is a y square by 2 del 2 w del x square and y square by 2 del w del x. So this is the new integral, or the approximate integral, that we are now interested in. And remember, this is for the neighborhood of 0. Now define sigma square epsilon. This is a new symbol. Sigma square epsilon as y square ky dy integral around that integral. So basically this y square and ky dy part here. So if I define that, what we get is, now this 515 was the integral that we are interested in, which is rewritten here. This whole expression. At the first round, I had these terms. Now, suppose I use the mean value theorem this way. So what I do is, for the first integral, I evaluate this second derivative at some point, take it out, and do the integration only on y square by 2. Same for this term also. So what will happen is, I will get this term del 2 w del x square to be evaluated at some particular point. This term also evaluated at some point, and the integral is exactly as defined, this half of this sigma square. So once again, we were interested in this original integral here in 512. We made some adjustments and used the Taylor series to come to 515. And then in 515, we use the typical mean value approximations define this new symbol to arrive at this expression, approximate expression for that integral. So there are several rounds of approximation, remember, because from the original expression, we first used the Taylor series, so that was some approximation. Then we use the mean value evaluated at x. That was another round of approximation. And we finally arrive at our approximate value for the integral in 516. So are you okay with that? Can you all check the two tricks that we have used? Both are, of course, very well known to you. The two tricks in sequential steps gives us a nice closed form expression for the integral. Starting out with 512, we arrive at 516. Is this okay so far?
Yes, sir.
So for our original problem, 511, we have taken care of the neighborhood of 0 part, 512. Now we want to look at the other remaining part, remember, which is an improper integral because we have plus infinity minus infinity involved. So that's the 513. So in part B, this is what we are going to handle, as in numerically approximate. So this region, mod y outside epsilon region, I have this integral as before. So we first write it out in two separate terms, one for the w difference, the other one for b to the power y. And here I can take this term outside because it is independent of y. And if I define this integral as w epsilon, then I can simply write 517 as this one integral in the difference of w plus del w del x into this omega epsilon term, where omega epsilon is this integral. Of course, evaluating omega epsilon will have its own challenge because this is also an improper integral. But given that the functional form is known, this can be done fairly precisely in numerical form. But the other part we have to handle properly, this difference. Okay. So then how far have we progressed? So what we have is, so we started out with equation 5.6, of course, this one here, after the change of variables. And we saw that essentially the challenge was in evaluation of this integral. The differential part we know how to handle. The integral was the challenge. So that integral challenge was split into two terms, near and far from 0. We approximate them separately and putting them together, what we get is, starting from 5.6, we have these terms, the sigma square epsilon involving terms for the 0 neighborhood integral. Then we have the smooth part. In the smooth part, I have also collected the del w del x coefficient from the integral so that it looks more compact. We have evaluated this omega epsilon integral that comes here, and finally this integral of the W difference is kept as it is, and everything equals 0. So once again, I collect terms with del W del X from the different integrals, put them together for compactness, write the other terms separately. So it is like our typical Black-Scholes setting. If you recall the Black-Scholes setting, the Black-Scholes also is an equation of this type, the first line, del W del tau, del W del X, and del 2W del X square, but with adjusted coefficients. So these adjustments came because we had integrals to handle. Then I have this RW. So a Black-Scholes result would stop with this term. So it will only have these first 4 terms. This additional integral is still remaining because we had the jump process to handle. So all these things together equals 0 is our new equation. And this is as far as we can go using analytical approximations, which we have done so far, Taylor series, mean value, etc. This is the simplest form, and this now has to be handled purely with a numerical approach. So we will take a minute and review whatever theoretical developments we have discussed so far. We started out with the SPIDE setting with appropriate mean adjustment, etc., using an explicit density for our jumps. So the integral for the value of the stock price, value of the derivative was manipulated, and then we use the risk neutral expectation to cancel some of the terms, show that some of the terms must be 0 to arrive at our PID 5.5. Then from 5.5 we did changes of variables, imposed the Neumann boundary conditions to get the new form 5.6. That was our new PID. In that PID, we said that we know how to handle the differential. So the troublemaker could be the integral, and this integral we have to handle properly because it is an improper integral, as well as there is a singularity at 0 because ky. We consider only very simple derivative contracts, vanilla put or call options. To handle the integral, we split it in 2 parts, near 0 and far away from 0. The near 0 term is approximated using Taylor series to give us this 5.16, and the region farther away from 0 is handled separately using mean value theorem. We modify it to 517. From 517 and 516, we finally get the simplified form of 5.6, the differential and the integral parts together in 519. So this was our journey so far. Okay, good so far. Can you all just quickly review this and see if there are any inconsistencies? So I will stop here today because this is rather cumbersome algebraic stuff. So better to do it slowly. But I still will ask you to check for consistency and tell me that it is looking consistent so far, because Friday we will then talk about the explicit discretization scheme.